A rigid body is a system of particles with a finite size that do not get deformed under the influence of any external force. The distance between any two particles of an ideal rigid body does not change even when it is under the influence of external forces. Let us now observe a bicycle in motion. If A and B are two particles on the frame, as the bicycle moves, the displacement is the same for both A and B. It implies that the velocity of particle A is equal to the velocity of particle B. This is also true with all other particles of the rigid body. Such a motion of a rigid body in which the velocity of all the constituent particles is the same at any instant of time is known as translational motion. Let us consider another rigid body, a door. Mark 2 points P and Q on the door and observe their motions as the door is opened or closed. When the door is in motion, do the 2 points P and Q have the same displacement? Their displacements are not equal. Hence, the motion of the door is not translational. This is known as rotational motion of a rigid body. The door is fixed to a line passing through the hinges. This fixed line about which a rigid body rotates is called the axis of rotation. When a rigid body is in rotational motion, how do the different particles on it move? When a rigid body is in rotational motion, every point on it moves along a circular path with the center on the axis of rotation, and the plane of this circle perpendicular to the axis of rotation. The rotating blades of a fan, the steering wheel of a car, and the Earth's rotation are some examples of rigid bodies in pure rotational motion. In all these examples, the axis of rotation is fixed and the rigid body rotates about it. Now, watch a spinning top. How does the motion of the top differ from that of the rotating bodies shown earlier? Here, the top is rotating about an axis. This axis of rotation of the top is not fixed, but rotates about a vertical line passing through its point of contact with the ground. This rotating axis forms an inverted cone, and this type of motion is known as precession. Even the motion of a grinding stone is of this nature. The axis of the grinding stone rotates about a vertical line that is normal to the base of the lower part of the grinding stone. In these examples, even though the axis of rotation is not fixed, the point of contact of the body with the ground is fixed. Observe the motion of the rolling wheel of a bicycle. The motion of any rolling body is a combination of rotational and translational motions. If a rigid body is fixed to an axis or a point, its motion is pure rotational motion. If the rigid body is free, it can have pure translational motion, or a combination of translational and rotational motion.
Let us consider a system of n particles with masses m1, m2, mi, mn, and the positions of these particles represented by x1, y1, z1, x2, y2, z2, xi, yi, zi, xn, yn, zn. The center of mass of a given system of n particles is a point in space. If the center of mass C is represented by the coordinates x, y and z, then x is equal to sigma mi xi by sigma mi, which is equal to sigma mi xi by m. Equation 1. Y is equal to sigma mi yi by sigma mi, which is equal to sigma mi yi by m. Equation 2. Z is equal to sigma mi zi by sigma mi, which is equal to sigma mi zi by m. Let this be equation 3, where m is equal to sigma mi is the total mass of the system. The location of the center of a mass of a system of particles depends on the locations of constituent particles and their masses. For example, consider two identical particles, each of mass 2 kg, located at points P of 2, 0, 0 and Q of 8, 0, 0. Since both particles are along the x-axis, even their center of mass lies on the x-axis. X is equal to sigma mi xi by m equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 2 into 8 by 2 plus 2 equal to 5. The location of the center of mass is C1, 5, 0, 0. Note that when masses of both particles are equal, x is a simple average of x1 and x2. What happens to the center of mass if the mass of the second particle is increased to 6 kg? x2 is equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 6 into 8 by 2 plus 6 equal to 6.5. The center of mass C2, 6.5, 0, 0, moves closer to the heavier mass. If we place one more particle of mass 4 kg at point R, 6.5, 6, 0, where will the center of mass of the three-particle system be positioned? The given set of particles are on the xy plane, and hence the center of mass also lies on the xy plane. On simplification as shown, we get x is equal to 6.5 and y is equal to 2. The position of the center of mass is C3, 6.5, 2, 0. On observing the above cases, we can regard the center of mass of a system of particles as the mass weighted average location of the constituent particles. In vector notation, the position of the center of mass of a given system of particles is given by R is equal to sigma mi/ri by m, where Ri is equal to xi into I plus yi into j plus zi into k is the position vector of the ith particle, and R is equal to xi plus yj plus zk is the position vector of the center of mass. If we take the center of mass as the origin of our frame of reference, then sigma mi into Ri is equal to 0. Here, the sum is a vector addition. This equation can be split into three equations. Sigma mi xi into I is equal to 0. Sigma mi yi into j is equal to 0. And sigma mi zi into k is equal to 0. In the two-particle example discussed earlier, with masses 2 kg and 6 kg, if the center of mass is chosen as origin, then x1 is equal to minus 4.5 and x2 is equal to 1.5. Sigma mi xi into I is equal to m1 into minus x1 plus m2 into x2, which is equal to 2 into minus 4.5 plus 6 into 1.5, which is equal to 0. When we deal with rigid bodies of continuous distribution of matter, we need to replace the summation symbol sigma in equations 1, 2, and 3 with an integral symbol. The coordinates of the center of mass of a continuous mass distribution is denoted by x is equal to 1 by m integral of x dm. Y is equal to 1 by m integral of y dm. Z is equal to 1 by m integral of z dm, where m is the total mass of the body. The equivalent expression in vector notation is R is equal to 1 by m integral of r dm. We can make use of symmetry considerations while finding the center of mass of homogeneous and regular shaped bodies. For example, let us consider a homogeneous ring of radius r on an xy plane. Let us position the origin at the geometric center of the ring. If we consider a small element of mass dm in one direction, because of reflection symmetry, there is an identical element of mass dm in the opposite direction. If the coordinates of the first element are x, y, then the coordinates of the other element will be minus x, minus y. When all these elements are added, we get integral of x dm is equal to 0 and integral of y dm is equal to 0. This happens only if the center of mass of the ring coincides with its geometric center. Based on similar symmetry considerations, we can prove that the center of mass of a thin rod, uniform disk, uniform sphere, and other such regular bodies lies at their geometric center. Let us consider a system of n particles, with its total mass constant with respect to time. Now, consider particle I from the system. In the graph, its position is marked by vector Ri, and the center of mass of the given system of particles is denoted as R. Then, R is equal to sigma MIRI by M. MR is equal to sigma MIRI, which is equal to M1 R1 plus M2 R2 plus M3 R3 and so on, plus Mn Rn. On differentiating both sides of the expression with respect to time, we get mdr by dt is equal to m1 into dr1 by dt plus m2 into dr2 by dt plus m3 into dr3 by dt and so on, plus mn into drn by dt. mv is equal to m1 v1 plus m2 v2 plus m3 v3 and so on, plus mn vn, which is equal to sigma mi vi. Let this be equation 1, where v is the velocity of the center of mass and vi represents the velocity of the ith particle. Let us discuss with an example. Consider a body A of mass 0.3 kg is dropped from a certain height. At the same time, another body of mass 0.1 kg is thrown up vertically from the ground with an initial velocity of 10 meters per second. Find the initial velocity of the center of mass of the system of these particles. For the body A, if mass of the body is ma, and for the body B, if mass of the body is mb, then ma is equal to 0.3 kg and mb is equal to 0.1 kg. For the body A, initial velocity Va is equal to 0. And for the body B, initial velocity Vb is equal to 10 meter per second. Mass of the system of two particles m is equal to ma plus mb. That is 0.3 plus 0.1 is equal to 0.4 kilogram. If the initial velocity of the center of the mass of this two-body system is vcm, then m into vcm is equal to mava plus mbvb, or vcm is equal to mava plus mbvb by m, which is equal to 0.3 into 0 plus 0.1 into 10 whole divided by 0.4 equal to 2.5 meter per second. On differentiating equation 1 with respect to time, m dv by dt is equal to m1 into dv1 by dt plus m2 into dv2 by dt plus m3 into dv3 by dt and so on, plus mn into dvn by dt. MA is equal to m1a1 plus m2a2 plus m3a3 and so on, plus mnan, which is equal to sigma of miai. Let this be equation 2, where a is the acceleration of the center of mass and ai represents the acceleration of the ith particle. Now, let us find the acceleration of the center of mass of the system of two bodies discussed in the earlier example. We will also describe the motion of the center of mass. Solution. If the downward direction is taken as positive and the acceleration of the center of mass is taken as a, then acceleration of a is equal to acceleration of b, which is equal to g. That means a of a is equal to a of b, which is equal to g. And m into a is equal to ma aa plus mb ab. Therefore, a is equal to 0.3 into g plus 0.1 into g whole divided by 0.4, which is equal to g. That means the center of mass of the system of two bodies will have downward acceleration g. Since the center of mass has initial velocity in the upward direction and acceleration in the downward direction, it initially moves up with decreasing velocity and reaches a maximum height and then start moving down. But miai is equal to Fi, equal to the net force acting on the ith particle. Ma is equal to F1 plus F2 plus F3 and so on, plus Fn, which is equal to sigma Fi. The net force on a particle may be an external force or an internal force. Fi is equal to Fi internal plus Fi external. The internal forces are exerted by one particle on another and forms action-reaction forces. F12 is equal to minus F21. The vector addition of all these internal forces acting on all particles adds to 0. Sigma Fi internal is equal to 0. Hence, Ma is equal to sigma Mi Ai is equal to sigma Fi external and is also equal to F external. Let this be equation 3. So, the acceleration of the center of mass A is equal to F external by m. What is the physical meaning of this equation? Ma is equal to sigma miai is equal to sigma Fi external and is also equal to F external. 1. The motion of the center of mass of a system of particles is independent of the internal forces. 2. the center of mass moves as if the whole mass of the system is concentrated at it and the external force is acting on it. 3. These conclusions are true for any system, a rigid body or a group of particles. When a spinner bowls, the ball may have a complicated rotational and translational motion, but the center of mass of the ball will have only translational motion. A gymnast performing an event on a pole will have a complicated motion, but his center of mass moves along a parabolic path. What about the linear momentum of the system of particles? We know that mv is equal to m1 v1 plus m2 v2 plus m3 v3 and so on plus mn vn, which is equal to sigma mi vi, as pi is equal to mi vi. mv is equal to p1 plus p2 plus p3 and so on plus pn, which is equal to sigma pi. But for a system of n particles, the linear momentum p of the system of particles is p is equal to p1 plus p2 plus p3 and so on plus pn, which is equal to sigma pi. Hence, p is equal to mv. Let this be equation 4. The total momentum of the system of particles is equal to the product of the total mass of the system and the velocity of the center of mass. P is identical to the linear momentum of the center of mass of the system of particles. On differentiating equation 4 with respect to time, dp by dt is equal to mdv by dt, which is equal to ma equal to F external. F external is equal to dp by dt. This is Newton's second law of motion applicable to the system of particles. If the external force acting on the system of particles is 0, then F external is equal to 0. dp by dt is equal to 0, and p is constant. This is the law of conservation of momentum applicable to a system of particles, which states that if the total external force acting on a system of particles is 0, then the linear momentum of the system is constant. A rigid body may have both translational and rotational motion. In such cases, it is usually convenient to work with the reference frame that is attached to the center of mass of the system of particles. The motion of a rolling wheel can be considered as translational motion of the center of mass and rotational motion of all other particles about an axis passing through the center of mass. As the moon revolves around the earth will also have the motion as shown to keep their center of mass fixed. When the motion of this system is influenced by the sun's attraction, the center of mass of this system will have pure translational motion.
If the product of two vectors A and B is a vector C, then C is called the vector product or cross product of A and B and is read as A cross B. the magnitude of the vector product C is equal to the product of the magnitudes of vectors A and B and the sine of the angle theta between them. When the value of theta changes from 0 to pi by 2, the value of sine theta changes from 0 to 1. And hence, the magnitude of a cross product changes from 0 to AB. What is the direction of vector product C? The direction of vector product C is perpendicular to that of vectors A and B. In other words, vector product C is perpendicular to the plane containing vectors A and B. There are two simple rules to determine the direction of a vector product, namely the right-handed screw rule and the right-hand rule. When a right-handed screw is placed perpendicular to the AB plane with its head on it and rotated from A to B through the smaller angle, then the motion of the screw indicates the direction of the vector product of A and B, that is, C. The other rule is the right-hand rule. Stretch the right-hand palm as shown and place a long vector A perpendicular to the AB plane. If the fingers can curl from A to B through the smaller angle, then the direction of the thumb indicates the direction of the vector product of A and B. Now let us study some properties of vector products. The vector product of two vectors is not commutative. That is, A cross B is not equal to B cross A. Although the magnitudes of A cross B and B cross A are equal. They are opposite in direction. However, A cross B is equal to minus of B cross A. Vector product is distributive with respect to vector addition. Consider three vectors A, B, and C as shown. Let's construct vector B plus C. And draw the vector product A cross B plus C. Next, let's draw the vector product A cross B and A cross C. Then draw a vector A cross B plus A cross C. This vector coincides with the vector A cross B plus C. Hence, the vector product is distributive with respect to addition. The vector product does not change its sign under reflection. That is, if we replace A with minus A and B with minus B, there will be no change in the sign of A cross B. What is the vector product of two identical vectors, say A and A? It is equal to 0, because for theta is equal to 0, sin theta is equal to 0. If we consider unit vectors I, j, and k along the three given axes, then I cross I is equal to 0. Similarly, j cross j and k cross k are also equal to 0. The vector product of I and j is equal to the product of the magnitudes of I and j. and the sine of the angle between them, which is 90 degrees. The magnitude of I cross j is equal to 1, since sine 90 is 1. The direction of the vector product I cross j is along the positive z-axis. Therefore, I cross j is equal to k. Similarly, we can prove the relationship between other unit vectors and their vector products. That is, j cross k is equal to I. K cross I is equal to j. J cross I is equal to minus k. K cross j is equal to minus I. And I cross k is equal to minus j. If the two given vectors, A and B, are expressed in terms of unit vectors I, j and k as shown, then the vector product of A and B is A cross B is equal to AXI plus AYJ plus AZK whole multiplied by BXI plus BYJ plus BZK. Upon solving and simplifying, we get A cross B is equal to AYBZ minus AZBY whole multiplied by I plus AZBX minus AXBZ whole multiplied by J plus AXBY minus AYBX whole multiplied by K. In determinant form, a vector product can be represented as shown.
Consider a rigid body in pure rotational motion about a fixed axis. As you have already studied, each particle of the rotating rigid body executes uniform circular motion. The center of the circular path is on the axis of rotation, and the plane of the circle is perpendicular to the axis of rotation. Observe a particle at P in the rigid body, that is, at a perpendicular distance r from the axis of rotation. Let O be the center of the circular path of the point. While the rigid body is in rotational motion, if the position of the particle is changed from P to Q during a small interval of time, delta t, then the angle POQ is called the angular displacement. In the SI system of units, angular displacement is measured in radian. In fact, when the rigid body is in pure rotational motion, the angular displacement of any of its particles is the same and is equal to the angle through which the rigid body is rotated about the axis of rotation. If the angular displacement of a rigid body is delta theta during a small time interval of delta t, then the average angular velocity of the particle is defined as the ratio of delta theta to delta t. The limit of this ratio as delta t tends to 0 is called instantaneous angular velocity and is represented by omega. Angular velocity omega is defined as the rate of angular displacement and is measured in radians per second. Note that the angular velocity is a vector quantity. If the right hand's fingers are curled in the direction of the rotation of the body, the direction of the stretched thumb is the direction of the angular velocity omega. When a rigid body is in pure rotational motion, the angular velocity of each particle is the same and is equal to the angular velocity of the whole body. If the angular velocity of a rigid body changes with time, it is said to be moving with angular acceleration. The rate of change of angular velocity is defined as angular acceleration, alpha. Alpha is equal to d omega by dt. In the SI system, it is measured in radians per second squared. This is also a vector quantity and its direction is along the vector d omega, which represents the change in angular velocity. Now, let us consider an example. When switched on, a fan attains its maximum angular speed of 30 radians per second in 12 seconds. When switched off, it takes 120 seconds to come to rest. What is the angular acceleration of the fan in both cases? In the case of increasing angular velocity, we get the angular acceleration alpha 1 is equal to 2.5 radians per second squared. In this case, both angular velocity and angular acceleration are in the same direction. In the case of decreasing angular velocity, alpha 2 is equal to minus 0.25 radians per second squared. Here, the direction of angular acceleration is opposite to that of the direction of angular velocity. For a better understanding, let us compare the terms related to translational motion and rotational motion. Observe a rigid body rotating about a fixed axis with an angular speed omega. Let v be the linear speed of a particle p, that is, at a perpendicular distance r from the axis of rotation. When the rigid body is in rotational motion, if the length of the arc traversed by the particle in a small interval of time is s, then s is equal to theta into r. On differentiating with time, ds by dt is equal to d theta by dt into r. V is equal to omega into r. This is a useful relationship between linear and angular speeds of a body. In vector notation, we can represent the relationship between linear velocity v and angular velocity omega as v is equal to omega cross r. This is applicable to a rigid body rotating about a fixed axis, as well as to a rigid body rotating about a fixed point.
What makes a body rotate? For example, what makes a door rotate? Yes, a force is required to rotate a door. Will any type of force be able to rotate the door? If the force acting on the door is parallel to the axis of rotation, it will not be able to rotate the door. There will be no rotation if the line of action of the force intersects the axis of rotation. Now, consider a wrench used to loosen a bolt. Compare the turning effect of the force when it is applied at different points from the point of rotation. The turning effect of the force is more when it is applied at a farther distance. Compare the turning effect of the force when it is applied at different angles. The turning effect is maximum if the force applied is perpendicular. The turning effect of a force is called torque or moment of force. As seen earlier, torque depends on the applied force, where it is applied, and how it is applied. Now let us define the torque of a force. If a force F is acting on a particle located at R, then the torque acting on the particle about the origin is a vector defined as R cross F and is denoted by the Greek alphabet tau. Now let us try to understand what torque is. Torque is a vector and its magnitude is expressed as tau is equal to Rf sine theta, where theta is the angle between R and F. The direction of tau is perpendicular to the plane containing R and F and can be found using a right-hand rule. If either the direction of R or the direction of F is reversed, the direction of tau is reversed. If the direction of both R and F is reversed, there will be no change in the direction of tau. The magnitude of torque can be written as tau is equal to R into F sine theta, which is equal to R into F perpendicular, or tau is equal to R sine theta into F, which is equal to R perpendicular F. R perpendicular is called the lever arm or moment arm. Note that the torque defined here is about a specific point, usually called origin. The torque of the same force about a different origin is different. Hence, identifying the origin is very important. Torque can be zero if the magnitude of the force is zero, or if the line of action of the force passes through the origin. The SI unit of torque is Newton meter. Note that the dimensions of torque and work are the same. The dimensional formula for torque is ml square t minus 2. Even though the torque and work have the same dimensional formula, work is a scalar, whereas torque is a vector. Now, let us study angular momentum. If R represents the position vector of a particle of mass m and linear momentum p, then the angular momentum of the particle about the origin is defined as the cross product of R and p. The magnitude of angular momentum of the particle L is equal to Rp sine theta, which can also be written as is equal to Rp perpendicular or R perpendicular P. L is 0 when r is equal to 0, or when p is equal to 0, or when theta is equal to 0. The SI unit of angular momentum is kilogram meter square per second. We can find a useful relationship between torque and angular momentum. We have L is equal to R cross P. On differentiating both sides with time, dL by dt is equal to d by dt of R cross P, which is equal to dr by dt cross P, plus R cross dP by dt. On simplification, tau is equal to dL by dt. The rate of change of angular momentum of a particle with time is equal to the torque on the particle. Now, we can extend the concepts for a system of n particles. The angular momentum of a system of particles about the origin is equal to the vector sum of angular momenta of individual particles taken about the same origin. This implies that L is equal to sigma Li, which is equal to sigma Ri cross Pi. On differentiating both sides of the expression with time and simplifying, we get dL by dt is equal to sigma tau I, where tau I is the torque on the ith particle of the system of particles. This is expressed as the cross product of Ri and Fi, where Ri is the position vector of the ith particle and Fi is the force on it. The net force on the ith particle may be external or internal forces exerted by other particles of the system. Thus, we categorize the total torque on the ith particle as the sum of torques due to external forces tau I external and torques due to internal forces tau I internal. As per Newton's third law, the forces between any two particles are equal in magnitude and opposite in direction and act along the line joining them. Due to this, the total torque due to internal forces, which is sigma tau I internal, becomes 0. The total torque on a system of particles is the sum of the external torques acting on the system. This implies that the rate of total angular momentum of a system of particles about the origin is equal to the sum of the external torques acting on the system taken about the same point. In many cases, we may have to calculate the torque on a particle about an axis. If AB is an axis passing through the origin, torque about the origin O, tau is equal to R cross F. If this tau makes an angle theta with the axis AB, then the torque about the axis is tau cos theta or R cross F cos theta. Now consider a rigid body rotating about a fixed axis. If the external torque on the system of particles is 0, then dL by dt is 0. This implies that the angular momentum L of the system is constant. The angular momentum of a rigid body is constant if the external torque acting on the body is 0. This is known as the law of conservation of angular momentum. The linear momentum of an aeroplane moving with uniform velocity is constant. Similarly, the angular momentum of the Earth about its axis of rotation is also constant. If the linear momentum and angular momentum of a rigid body do not change with time, it is said to be in mechanical equilibrium. We know that the linear momentum of a rigid body is conserved when the net external force acting on the rigid body is zero. That means an aeroplane moves with constant momentum if the resultant of all the four forces, weight, lift, drag, and thrust acting on it is zero. In such a case, the plane is said to be in translational equilibrium. A body is in translational equilibrium if the net external force acting on it is zero. Similarly, the angular momentum of the rotating Earth is constant because the net external torque acting on it is zero. We say that the Earth is in rotational equilibrium. This means if the vector sum of all the torques acting on a rigid body is equal to zero, then it is said to be in rotational equilibrium. Using this understanding, we can list the conditions for a rigid body to be in mechanical equilibrium. A rigid body is said to be in mechanical equilibrium when the net external force and the net external torque acting on it is zero. That means a rigid body is in mechanical equilibrium if sigma Fi is equal to 0 and sigma tau I is equal to 0. Now look at the glass. It is at rest. It is in mechanical equilibrium because the net force and the net torque acting on it is 0. If a body in mechanical equilibrium is at rest, then the body is said to be in static equilibrium. We know that the torque acting on a particle depends on the location of the origin. If the origin changes, the torque on the particle also changes. Then what about the condition for rotational equilibrium? Will it also depend on the location of the origin? If the condition for translational equilibrium, sigma Fi, is equal to 0, holds good for a rigid body, then the condition for rotational equilibrium, sigma tau I, is equal to 0, is independent of the location of the origin. For example, the ladder shown here is in static equilibrium. This means sigma Fi is equal to 0 and sigma tau I is equal to 0. There are 5 forces acting on the ladder. F1 and F2 are the frictional forces. R1 and R2 are the 2 normal reaction forces. And W1 is the weight of the body. As the ladder is in static equilibrium, the vector addition of all these forces must be equal to 0. As the condition for translational equilibrium holds good in this case, we can calculate the torques about point A or about point B or about any other point to compute sigma tau I and to equate it to 0. Note that the equations sigma Fi is equal to 0 and sigma tau I is equal to 0 are in vector notation. Each of these equations is equivalent to 3 scalar equations. In scalar notation, equation sigma fi is equal to 0 can be written as 3 independent equations. Sigma fx I is equal to 0. Sigma fy I is equal to 0. And sigma fz I is equal to 0. And the equation sigma tau I is equal to 0 can also be written as 3 independent equations in scalar notation as sigma tau xi is equal to 0. Sigma tau yi is equal to 0. And sigma tau zi is equal to 0. A body is in mechanical equilibrium if these 6 independent scalar equations are satisfied. Now let us consider a special case where all the forces acting on a rigid body are in the same plane as the xy plane. Since all the forces are in the xy plane, the component of force along the z-axis, Fz, is 0. Since forces in the xy plane cannot produce torques in the same plane, we can write tau x is equal to 0 and tau y is equal to 0. In such cases, we need not consider all the 6 equations discussed above to find out whether a rigid body is in mechanical equilibrium. Instead, the body will be in mechanical equilibrium if the following 3 equations are true. Sigma fxi is equal to 0. Sigma fyi is equal to 0. And sigma tau zi is equal to 0. What happens if the net force acting on a body is 0, but the net torque is not 0? In such cases, the body is said to be in translational equilibrium, but not in rotational equilibrium. The body exhibits pure rotational motion. If 2 equal forces act on a body in opposite directions, the net force is 0. But if they act at different points, they can produce torque, as in the case of a couple. 2 parallel forces that are equal in magnitude and opposite in direction, acting on a rigid body with a different line of action, forms a couple. For example, a couple is needed to rotate a steering wheel, or to open a tap, or to make a carom striker rotate. Moment of couple tau is equal to r cross f, where r is the perpendicular distance between the 2 forces. Let us consider a lever placed on a pivot. Let the effort F1 and load F2 be the 2 forces acting on the lever perpendicularly in the downward direction, and R be the force exerted by the pivot in the upward direction. The distance between pivot point and the point of application of effort is called the effort arm, R1. The distance between the pivot and the point of application of load is called load arm, R2. The lever is in translational equilibrium. R minus F1 minus F2 is equal to 0. Equation 3. If we calculate the torques acting on the lever about the pivot point, we have tau 1 is equal to R1 F1. This is positive because tau 1 is an anti-clockwise torque. tau 2 is equal to minus R2F2. And tau 2 is negative because it is a clockwise torque. Since the lever is in rotational equilibrium, tau 1 plus tau 2 is equal to 0. R1F1 is equal to R2F2. Equation 4. This means for a lever, effort into effort arm is equal to load into load arm. This statement is known as the principle of moments for a lever. Equation 4 can be used to find the mechanical advantage of a lever. Mechanical advantage is equal to effort arm by load arm. The balancing bird shown here is in static equilibrium. That means net force and net torque acting on it must be 0. We know that there are two forces acting on the bird. One is the gravitational attractive force, that is, the weight of the body in the downward direction, and the balancing force N in the upward direction. Since the bird is in static equilibrium, these two forces must be equal in magnitude, opposite in direction, and must act along the same line. How is it possible that the whole weight of the bird acts through a point at the tip of its beak? Let us try to understand this by taking a rigid body. A rigid body can be divided into smaller mass elements of masses m1, m2, so on, mi, and so on, mn. The weight of the rigid body must be equal to the sum of the weights of these small mass elements. If the weight of the ith particle is Wi, then W is equal to sigma Wi. The weights of these mass elements produce gravitational torque on the body. We can always find a point such that the total gravitational torque about the point on the body due to these mass elements is 0. For example, if G is a point and R1, R2, Rn are the position vectors of different mass elements with respect to G, then the torques due to the weights of small mass elements about G are tau 1 is equal to R1 cross W1, tau 2 is equal to R2 cross W2, and so on, and tau n is equal to Rn cross Wn. If the torque due to the weight of the whole body about G is called the total gravitational torque, tau G, then tau G is equal to sigma tau I, which is also equal to sigma Ri cross Wi. If the point G is such that sigma tau I is equal to 0, then G is called the center of gravity of the rigid body. The center of gravity of a rigid body is defined as that point where the total gravitational torque on the body is 0. The weight of a rigid body is the sum of all these small weights and acts through its center of gravity. When torque is calculated about the center of gravity, weights of some mass elements produce clockwise torque and of others produce anti-clockwise torque, making the net turning effect is 0. Hence, the weight of a rigid body can't produce any net torque about its center of gravity. Torque due to the weight of a body about any point can be calculated by assuming the whole weight of the body concentrated at its center of gravity. For example, consider a rigid body of mass 2 kg with its center of gravity located at 5, 2. If the weight of the body is along y-axis, find the torque due to its weight about the origin and also about its center of gravity. The weight of the body W is equal to mg is equal to 2 into 9.8 is equal to 19.6 Newton. The gravitational torque tau g is equal to R perpendicular into W is equal to 5 into 19.6 Newton meter is equal to 98 Newton meter and acts perpendicular to the plane of the paper and passes into it. As the weight of the body acts through its center of gravity, torque due to weight of the body about its center of gravity is 0. We can balance this rigid body by applying an upward force equal to its weight and passing through its center of gravity. The bird shown earlier is designed in such a way that its center of gravity is located at the tip of its beak. Hence, we are able to balance the bird by applying an upward force at the tip of its beak. How are the two terms, center of gravity and center of mass, different? In the equation, tau g is equal to sigma tau I, which is equal to sigma Ri cross Wi. Wi is the weight of the ith particle and is equal to mi into g. Then, tau g is equal to sigma Ri cross mig, if g is same for all particles. Then, tau g is equal to sigma mi Ri cross g. That means, if tau g is equal to 0, then sigma mi Ri is also equal to 0. Tau g is equal to 0 only when the origin coincides with the center of gravity. Similarly, for a system of particles, sigma mi Ri is equal to 0 only when the origin coincides with the center of mass. The two concepts, center of mass and center of gravity, are two different concepts. If the acceleration due to gravity is the same for all particles of a rigid body, then the center of gravity coincides with its center of mass. For bodies of small size, the methods used to find the center of mass can also be used to find the center of gravity. We have another useful method to find the center of gravity of a rigid body of uniform thickness. Take the body and mark 3 points A, B and C at 3 positions as shown. Suspend the body from A and draw a vertical line AA1 as shown. Suspend the body from B and draw a vertical line BB1 as shown. Suspend the body from C and draw a vertical line CC1 as shown. The intersecting point of the 3 lines is the center of gravity of the body.